Hello everyone, this is Vikram and welcome to my channel. This is part 3 of our common AIML terminology series that we started. In the previous video, we talked about tokens, embeddings, inference, and how transformers and self-attention works. We also understood hyperparameters, overfitting, guardrails, and all those things. In this video, we'll understand the current LLM limitations and how do we overcome them. We'll start with basic introduction of RAG, and then we'll deep dive into each and every uh, you know component inside RAG, like knowledge bases, chunking, and various chunking strategies. We'll understand embeddings and embedding models and cosine similarity, semantic search. Then we'll move on to vector databases and why these are needed. And then we'll understand what is RAG ingestion pipeline, retrieval and reranking. We'll also understand a bit about hybrid search, not in detail. And then we'll see the end-to-end RAG flow. Then we'll move on to MCP. What is MCP? Various pillars inside MCP, like tools, resources, and prompts. We'll also compare RAG and MCP, and then we finally move on to understanding the difference between RAG and difference between AI agents and agentic AI. Then at the end, we'll understand a bit about reasoning in AI. Let's start with how LLMs work internally. We already covered this in our previous session. Whenever we ask any question to your LLM like ChatGPT, for example, the question is, what is capital of France? Then what will happen is, inside the whole LLM, we have tokenizer, which will convert each token. Basically, token is a word, or it can be part of the word. So the entire text is broken into individual tokens, and tokenizer will assign token IDs. Basically, this is part of tokenizer to have vocabulary where each word will have a specific token ID associated with it. And then these token IDs are sent to the model, and model has an embedding matrix, which is a lookup table containing the the token ID and the associated vector. Again, these vectors are learned during the process of the training, so for every word there is an associated vector. So how this works with respect to the user question is, when the user asks any question, so these vectors are fetched, and for the question all these vectors are sent to the embedding, like the neural network. So the neural network, through the process of self attention, understands the overall the question. We already talked about what is self attention. So basically all the vectors related to question are sent to the the neural network, which is your model, and finally the output is generated in the form of tokens only. And then these tokens are again sent to the tokenizer to convert them back to the the actual words. For example, for this question, what is capital of France? We get Paris is France capital. So this is what shown to the user. Okay, but there are certain limitations for these LLMs. For example, even though large language models are very powerful, there are certain limitations that affect their reliability and usefulness in production systems. First one is knowledge cutoff. We all know that LLMs are trained on huge data, but they cannot access the real-time data or the recent data, because during the process of the training we only take the data probably for till a particular year. For example, if I'm training today, so the model will have all the data until today, but not what will happen tomorrow. Of course, like if I ask question tomorrow, anything related to the current scenarios, like it may not be able to answer. That is called knowledge cutoff. The other one is hallucinations. LLMs can generate answers which may be factually incorrect, but they sound very genuine to the user. In this case, what is actually happening is LLM is hallucinating. So LLM doesn't know the answer, but it is giving some made up answers which can be which can seem very true. Okay. And then context window limits. We already know what are context windows and limits. This is the maximum number of tokens an LLM can process in a single request. For example, like I can ask a simple question, or I can send a complete ebook in the form of text or PDF. So this is what the context window is. So LLMs have certain context window limits. Beyond that, if you try to, if beyond that, if LLM try to process that request, it can lead to errors or truncations or hallucinations. And then LLMs don't have access to your private data. So if you ask ChatGPT about your company's internal data, it may not be able to answer because it has no access to the, the private and confidential information of the organization. And the other one is lack of reasoning depth. Of course, this is not very true for the recent LLMs. So we can discard this. LLMs have uh, you know s- I mean a level of reasoning depth where they can understand the overall intent of the question, and they can use multi-step approaches to basically achieve a goal. And the last limitation of LLM is ability to take any actions. For example, if you ask ChatGPT to modify your local files, it may not be able to do. But of course, if you use tools like Codex or Cloud Code, since they run locally in your machine in the form of a CLI tool, they have ability to do modify the files. But if you use ChatGPT or any the desktop applications, they may not be able to directly modify your code, and they will not have ability to call external APIs or execute code. uh, all these features are missing from LLMs. For example, let's take a small example. So I asked LLM what were our total sales in Q1 2024. If you see, LLM has generated the response, but this response is completely made up answer. In this case, LLM is hallucinating. The reason why it did not give me the proper answer is because it has no access to my company's internal data, because I did not provide it any sort of access in the form of APIs or anything like that. So even though my Q1 2024 sales is 87.6 million, it has given 52.4 million because it did not have access to my internal company data. And one more example, if I ask ChatGPT or any other LLM, how many casual leave days am I entitled in a year, you can see it has given me a very generic response. So it says, like, typically it will be like 6 to 12 days, or it can be like 8 to 12 in case of any government jobs or private sector jobs. But it is also suggesting, if you want the actual leave days, so you need to check the employment contract or any handbooks or any HR related policy documents, right? But it has not given me my actual leave days I am entitled for, right? Because it has no access to my internal company related data. That data can be in the form of some confluence pages, or it can be PDFs or docs that my company maintains in their own, probably some portals, right? How do you overcome these LLM limitations, like lack of having company related data or inability to do any actions other than just generating text? So there are several techniques. The techniques like RAG, we can provide LLMs access to the internal documentation or some sort of knowledge apart from the knowledge that it already has, right? And then you can also give LLMs an ability to use tools like calling external APIs or run code or query databases. It is like giving LLMs ability to take action, not just generate the text. And then fine tuning. So fine tuning is a method where you take a model and then tune it on more data. So the data can be company related data. So what happens is, once the model is trained with internal data, so it can give answers for the questions related to the company's information, right? But the problem is, like, in case if the data changes, you need to keep on tuning this model. The other one is prompt engineering. So by carefully designed prompts with examples and instructions, it can give more relevant and high quality outputs. And then using agentic patterns, the model can reason itself and achieve a specific goal using multi-step planning and execution. The last one is model context protocol, which gives LLM the ability to talk to external tools, read the data, take actions, right? These are all the techniques that we use to overcome the the LLM limitations. For example, like I can use RAG to access internal companies documentation, right? Documents. For example, when a user asks this question like how many casual leaves am I entitled for in a year, so using retrieval augmented generation I can access various sources inside my organization that has information about the leave policy or HR policies or anything like that. So by getting information from all those source, LLM now has information about those things, right? But the problem is like the question that the user asked may present in more than one document. So all these documents becomes a context for the LLM. So now LLM takes this context and then produces answer by taking the sources from these documentation, right? And also in this case LLM can also give you from which document it has given the answer, right? So this is like kind of like grounding the LLM responses. So instead of LLM hallucinating and giving random responses, in this case LLMs after generating the response, it will also give you the source of the information, right? This is a typical RAG. But for understanding RAG we need to understand a lot of things, so let's start those concepts one by one. So retrieval augmented generation is a technique that enhances LLM's response by retrieving relevant external documents and using them as context before generating an answer. So before LLM actually generates an answer, it gets the context, right? So the whole process is retrieval augmented generation. Of course we'll understand what is augmentation, what is retrieval and generation. Why RAG is important is it reduces hallucinations by grounding the responses in actual source document. So LLM now if it has to respond, I mean like once it responds, it also gives the source of that response, right? From which document it has taken that response or the information from, not the response. And using RAG you can provide up-to-date information beyond the LLM's training cutoffs. Of course the LLMs LLMs, let's say you take an LLM that is trained or having the knowledge cutoff of 2024, but using retrieval augmented generation you can still get up-to-date information because LLM is now getting the context from external documents. And using RAG, you can access private or proprietary data without fine-tuning the model. You don't have to tune the model. You take any base LLM and use RAG techniques to get the relevant responses, right? Yeah. So there are three pillars in RAG, which is retrieval augmented generation. We'll understand like who does this retrieval and augmentation later, but definitely this is not the role of LLM. So LLM doesn't retrieve, LLM doesn't augment. You have to do all the framework like LangChain or Llama Index, and any other library has to do this process and then only give it to the LLM. Okay. So for example, when a user asks question like what is the probation period policy for the new employees in your organization, so LLM doesn't go through the process of reading the external documents and all, but there is a different way. So let's start with retrieval. What is the retrieval is? Retrieval will basically search for the relevant information from the knowledge bases. That is called retrieving. So retrieving information, not every information, okay, but retrieving the information which is for this particular question, right? So it takes the reference from knowledge bases and vector databases. Again we'll understand this. So retrieving is retrieving the knowledge from the knowledge sources, and once it is retrieved, like, of course it will not retrieve information from all the documents, right? Okay, it may have thousands of documents, but for this particular question it the retrieval may find relevant information in only 5 to 6 documents. So all the 5 to 6 documents, there is a things get little confused here. here not all the documents are sent, but only the part of the information from those documents is sent, right? So for this question, so the retriever has retrieved some information in the form of various like data, like some passages, or we usually call them as chunks. Okay, so you can see it has retrieved probation period is 6 months from date of joining, performance is reviewed during probation, confirmation is based on satisfactory performance. And these retrieved results or context is not from single document. Okay, probably this is coming from HR policies, this is coming from employee handbooks, and this is coming from some other document that outlines companies guidelines and all, right? So what is the process of augmenting is it is enriching the query by adding more context. So for this user, so usually without RAG, what happens is this entire query will be sent to the LLM, right? But here the user query will be added with the context, and this whole thing is sent to the LLM. Now LLM has the question and it also has the information. Okay, but you can ask a question like, if I already know the answer, so why would LLM again need this input? Why don't the RAG system itself give me this result back to the user? Okay, but the problem is here, the context that is retrieved may not be properly or grammatically aligned, right? It may not be it cannot be properly understood by the user, right? In this case, LLM has to take this context and then generate a response which is kind of organized. Okay, so in this case, augmenter will take the user query, add this context and send to the LLM. Now LLM will generate the response. So the response is completely structured, grammatically correct, and it is easily understood by the user. So now what LLM is responding is the probation period for new employees is 6 months from date of joining, and then you can see it has completely rewritten it or summarized it in a better way that users can easily understand. And one more thing here is RAG will also provide the source of the information. So it will give you from which source it got this response from. Like the source can be more than one, but it will also give you the probably the links or the name of the documents from which it got the answer, right? So this is retrieval, augmenting, which is enriching, and then generation by the LLM. Okay, so the common question that usually we get is, do LLMs use RAG? Like, will LLMs do the actual retriever augmentation? No. So basically LLMs aren't that smart enough to know what it doesn't know. Okay, for example, if I ask this question to the LLM will basically give me a generic answer. Okay, so it doesn't know whether the answer it is giving it is right or probably related to the internal policies, right? But it will always generate the response, but the response may not be very suitable for you. Okay, so that's a reason LLM doesn't actually use the RAG. Okay, so the RAG system is designed upfront to always retrieve the information from the knowledge base. So even before the user query reaches the LLM through explicit program or through some frameworks, we always use the RAG technique. That is, we always retrieve the data from the knowledge bases, right, before generating the response, right? And when the user asks a question, okay, so the retrieval mechanism automatically kicks in and gets the context, right, from the knowledge bases. The LLM doesn't need to recognize its own knowledge. Basically, the system is pre-configured to fetch the relevant information regardless. Okay, the RAG system itself is designed like that. The RAG process happens before LLM even gets the question, right? So it is always on retrieval. So for every question, you always retrieve the information from the knowledge bases before LLM even answers your question. So that retrieved context is sent to the LLM with the original query to get the final response, right? So this is not done by LLM. So this is an explicit programming that we do. Okay, now we talk about knowledge bases a lot. What are knowledge bases is, it is basically a collection. Okay, so it is not a folder or something like that. Okay, so it is just a collection of information. It can be internal documents, or it can be external documents from public internet. Okay, so internal documents like HR policies, employee handbooks or run books, training materials, FAQ documents, or some readme files. External documents can be some research reports, news and market updates. So combinedly all these, we call it as a knowledge base. Right, yeah, so we call this as a knowledge base. So AI, the RAG based applications uses this knowledge base to get the relevant context. Okay, now what is chunking? Okay, so before understanding chunking, so there is a whole process of RAG, so which involves the knowledge bases, and then we also have to understand the vector databases even before the retrieval augmented generation kicks in. Okay, so what is the process of chunking is, chunking is a process of breaking large documents into smaller meaningful segments, also known as chunks. The reason why this chunking is required is, for example, if there are, let's say, 100 documents in my company's organization that talks about all the policies and all. Okay, so if I have to, and more than one document will have some common information, right? More than one document can talk about employee provision and all those things. If I have to get the information of employee probation period, I have to compare all the documents, right? So documents can be big in size, probably like each document can be like 50 or 100 page PDF. So how do an LLM even read those documents which are huge in size every time when the user asks a question, right? It's practically impossible. That's the reason why we break those documents. Okay, so when we talk about chunking, so it's not breaking one document into one chunk. A single document, for example, it's a PDF file of 50 pages. Okay, so each page can be a chunk, or one page can be broken into two chunks. Okay, which means like for 50 pages I can get 100 chunks, right? Or more than that, right? So likewise, like if I have like many PDF files or many documents, which we commonly call as knowledge bases, so every document is broken into smaller segments, chunks. Okay, so now the chunks will hold certain information, right? How do we break them and all, we'll see it later. But we have to chunk these documents so that why chunking usually matters is LLM will have context window, right? So I cannot for generation of the answer which we talked about in RAG, I cannot send a whole 50 pages PDF to the LLM, right? Because LLM has context window limits. It cannot extend this context, right? And also smaller chunks enable more precise retrieval. Okay, if I break them into multiple chunks, so I can easily compare the query, like what user is asking, and find the relevant chunks. Because these chunks are smaller in size, it is very easy to find and retrieve proper like relevant information. Okay, now coming to the chunking, so as we already discussed, if it is a 50 pages PDF, I can break one page and I can say it as a chunk, but it may not be true all the time, right? For example, one of the chunking strategies is fixed size chunking, where I take a document and then I break it into chunks based on the number of tokens. For example, I'll say uh, break the document for every 100 tokens. So for every 100 tokens, which are nearly the 75 words, so for every 75 words it will break, like every 75 word information is a chunk for me. For example, if this is an original text, you can see here it is breaking into multiple chunks. But the problem with this approach is, usually each chunk should be very meaningful, right? But if you look at this chunk, RAG systems combine large language model with external, but here there is no information after this chunk, which means this is a chunk but it is not actually carrying a meaningful information, right? Recursive character chunking, in this case, what you do is you split the documents into paragraphs and then into, uh, you know, other sentences. So if you see this whole text, this is the original text. If you see, so I'm first converting into paragraphs and then individually I'm converting them into sentences, right? This is also one more method, but the one method that I really like is semantic chunking. So what is semantic chunking is, for example, if you take this particular text, so this text is coming from a document or a knowledge base, okay, so I can break it into chunks which are meaningful. For example, I can just break my or get the first chunk till this point. So RAG system combine large language models with external knowledge sources. So this is a meaningful sentence. So this can be a chunk. For example, the next one can be a chunk because it has certain meaning to it. So semantic chunking does the same thing. So it understands the whole text inside the knowledge base, and then it will break the information which are which carry certain meaning, like the semantic meaning, right? This is the one of the best chunking strategies. So there is also document based chunking. For example, if I have a markdown file, okay, so it has all these markdown tags. So what I can do is I can break the you know these markdown documents for every tag. So this is one of the tag, so this convert into a chunk, convert into a chunk, convert into a chunk, something like that. But if I have like text document, what I can do is these are all various paragraphs. So what I can do is I can do paragraph based chunking as well. So these are all logical based chunking, right? And then agentic chunking involves using another LLM, okay, to determine where should we split the information or the documents, right? Since LLM knows or understands the overall sentence, so it can do a very effective chunking. So now you can see it did not chunk randomly. It uses its own knowledge to break chunks that has semantic meaning, okay. So now if you go back to the overall flow, so we know the documents are the knowledge sources, and then we break them so that we get very small chunks that are meaningful, and then we don't run into context level context limits, okay. Now let's understand what are embeddings. Okay, the embeddings are dense numerical representations of tokens. Okay, we already discussed this in the previous video. So you take a word or you take a sentence and then convert into a vector. Okay, of course, like LLMs during the process of training, they get these embeddings learned. So for if you take the case of car, it has certain embedding for it, and then Honda has certain embedding, and then Apple has certain embedding. If you try to plot them in the vector space, you can see Honda and car are very close to each other because Honda and car are related to each other, and this is basically learned in the process of training, and the model will assign vectors so that car and Honda are very close to each other. It usually does this during the extensive training and seeing car and Honda across multiple documents from the training data. Okay, but Apple here, it has plotted it somewhere far in the vector space because both of like, these three are not related. But if you have a banana and then if you have vector for it, and if you try to plot, you will see that both of them are very close to each other, because this is what embeddings are. Words with similar meanings have vector that are very close to each other. Okay, so remember why we are talking about like words or sentences which are having similar meanings are close to each other, right? So this is called semantic meaning, right? So this is what powers the RAG. Okay, now who does this embeddings is the LLM, but we don't use the inbuilt LLMs embedding to LLMs embedding in RAG systems always use the external embeddings, because if you see the RAG flow, we are not talking to the model directly, right? First we get the relevant context, and then only we send that context, like the augmented prompt, to the model. So that's the reason why we don't use the LLM for generating the embeddings. Okay, we use external embedding models. Of course there are other reasons as well. Using embeddings of model can be costly, but using external embedding models can be quite easier as well. So RAG systems uses external embedding models. These models convert text into numerical representation, as we already said, and while converting, it will try to place the vectors with similar meaning close to each other. This will be used for semantic search. Okay, what is semantic search? Is finding the documents or information which are close to each other in the form of meaning, right? Even in RAG. Okay, so we use the embedding models to find the information which is relevant for the user query. Okay, you'll understand it, how embedding models will be used in the coming slides, even for clustering and classification, because embedding models will try to place the vectors or words which have similar meanings close to each other in the vector space. We can form the clusters. So basically the words with similar meanings will be very close. It looks like a cluster, and we can classify certain data, right, using embedding models. Even recommendation systems. So if you watch a movie on Netflix or some other video streaming platforms, so based on similar users watch history, you'll also get those recommendations, right? Yeah, so this is an embedding model which takes in the data. So the data can be text or multimedia input as well. For example, if I just give this information like a car is a fast vehicle, so embedding model can convert into vector. The other chunk, it has converted into vector. The third one, it has converted into vector. Now if you see, the vectors between A and B are very similar, or they seem to be very close to each other. The reason is they have very similar meaning. A car is a fast moving vehicle, and then a bus moves quickly. So car and bus, they are very close to each other because because they're very close to each other, because both of them are modes of transport. But flowers grow in gardens is not very close to the two sentences, and of course it gets a different vector. So there are many external embedding models that you can use. You can find multiple embedding models in Hugging Face, and then for OpenAI you have text embedding 3 small, text embedding 3 large. You also have from Cohere embed English v3.0. Of course these may not be the recent ones, so you have to check the provided documentation for any sort of latest models. Okay, now how do we know that two vectors or 2 points in vector space are close to each other, or they are similar? Okay, so we use a technique known as cosine similarity. Okay, so it finds the angle between two vectors, not the magnitude, it's only the direction. So we find the cosine angle between these two vectors. For example, this is 1 point, this is 1 point. Okay, so I'm saying this is a cat and this is a dog, which are 2 points in the vector space. Now how do I know that the cat and dog are similar? So I find the angle between both of these, that is cos the cos theta. And if the angle is 0, which means both of them are in the same direction, right? So in that case, if the angle is 0, we say that they are very similar. If the angle is 90 degrees, these are not similar, right? For example, take the case of car and banana. So okay, if you try to see their vectors in the 3-dimensional, I mean like the n-dimensional space, they have 90 degrees angle, which means they are not they disappear, right? Sorry, dissimilar. Okay, but if you get an angle like the perfect opposite direction of 180 degrees, then we say that they are perfectly opposite, which means these are not at all related. For example, the word good and bad, they are not at all related. So if you try to find the angle between the vectors, you'll get, it's not exact 180. This is just an example, but I'm trying to say that these two words are not similar by looking at the angle between these two, right? Coming to the previous example, if you look at the angle between A and B, you can see it is near 0. So which means, they are somewhere like very close to each other, something like that. I mean, like these sentences. For example, this is a car is a fast vehicle and this is the bus moves quickly. So the vectors are very close to each other, because when we try to find the angle between them, so they came as 0.115. But if you check the case of A and C and B and C, you can see they are almost equal to 1, which is they are not related to each other. Okay. Semantic search is a I mean, this is a core building block of retrieval augmented generation. So the main idea of semantic search is to find the documents which have similar meaning, right? For example, again it works in a different way. So how do I find the similarity? Again, it is a little bit different topic, because I have to convert user query into also an embedding. But as we already discussed, in order to find the similarity between two vectors, so it is only done through vectors. Okay, like I can't take a user text and I cannot compare it with a vector, so both of them should be vector. Okay, so semantic search is about finding the documents that have similar meaning. For example, I asked a user, how can I reduce high blood pressure naturally? Okay, and inside my so don't think about vector databases for now. So let's say this is my vector space. Okay, so where I have many vectors that talks about blood pressure or some medical related issues. Okay, so now how do I get the answer for this, right? So first, in order to compare the similarities, this input itself should be a vector, right? So this is called query embedding. Okay, so a user query itself is converted into an embedding. Okay, now within the embedding space, what I'll do is I'll try to find the similar documents that talk about this one. This is usually done through semantic search. Okay, so I find the vectors which are very close to each other. For example, all these vectors are very close to each other for my query, so which means all these vectors may have the information that I am looking for, right? But there are other vectors which are far and may not have the needed information, right? Now once I find the information, so these become the results, right? Okay, so this vector has information about talking the ways to reduce the blood pressure. Some this document is talking about lifestyle changes. This document is talking about the herbal remedies. So all these are vectors which are very very close to my the query, right? Yeah. Vector databases. Now I know that for semantic search I have to compare the vectors, right? But where do these vectors usually get stored? Okay, of course I cannot store them in my local machine, right? So there are specialized databases that store, index and search high dimensional numerical vectors. Okay, while a normal database will store the data in the form of these tabular values. Okay, for example, you can see this is a perfect table, right? uh, the vector databases store the embeddings. Okay, so if you want to know the difference between a normal database and vector database, for example, using an SQL or structured query language query, if I ask the database to give me all products with price $50, you can see it is giving me the output as t-shirt and sock, because the query is matching the $50 that I need. But in case of vector databases, they directly don't work on the exact values. Okay, so they work on the semantic search. Okay, so they find the documents or the information which is very relevant to the user query. For example, give me product semantically similar to comfortable running shoes. Now what my vector database can give me is, since vector database already has information of all the products. Okay, and these databases don't store the images and all that stuff. We only talk about embeddings, right? So now for the user query, you can see we are talking about comfortable running shoes, which means running shoes, comfort sneakers may not be true, but the walking shoes and then the trail running shoes all can be the output of the vector database query. The reason is the user query itself is converted into vector because I have to find the similarity. Okay, I am not finding the data exact data in the sense comfortable running shoes. If you see, there is no such product as comfortable running shoes. There are running shoes and then there are walking shoes, but I need to find the relevant data for this query. Okay, so the query is converted into the embedding. So this embedding is compared with all the embeddings in the vector database. Okay, so this one and this one and this one, uh, maybe this one will be may not be true. So running shoes and then trail running shoes, probably this is the wrong, but it will compare the other vectors and it will find the closest vectors for the user query and it will give you the responses. So this is semantic search. So vector databases retrieve data based on the semantic similarity, not the exact keywords or not the exact value. Okay, as we do in the normal databases. Okay, now what is this vector database? So the vector database usually stores only the embeddings from the knowledge bases. Okay, so if you go back to the the previous image that we saw, so first we have the, excuse me, so first we have the documents and then we chunk them, and then through embedding model we convert into vectors and then we stored in the vector databases, right? This is the whole method, right? Now we have a lot of chunks and then we convert into embeddings and then we store them in the vector databases. What exactly gets stored? It is only the embeddings? No. So vector database stores a lot of things. Okay, so first the vectors themselves. So for every chunk you get a vector, so all these vectors are stored. Okay, and also we store the metadata. So what is metadata? Is it is data about a data. Okay, it's a data identifier. Okay, so basically, if I just store the vector, I may not have very good information of that vector, so I need to have a metadata associated with that vector. For example, um, you know this vector may be for a specific chunk. So the process is like doc and then you chunk and then you embed and store in the vector database, right? So here for this particular vector I can also store the metadata, like what is the doc, okay, what is the chunk from that doc, and what is the page number from that doc from which the chunk is created, and from that chunk the embedding is created, right? So this is metadata, and also the timestamp or the category. Okay, so it is information of that vector, from where that vector is coming from which chunk, and what is the source of that chunk, right? And also, along with the vector, I'm also storing the content of that chunk and the associated vector. So this is the original text plus the vector. Okay, so these are all get stored inside the vector database, not just the vector. Okay, so each vector data and database entry can have the embedding, the original text, and then the metadata associated with, which means it has everything of your entire knowledge base, right? So which means if it is generating an answer from a particular for a particular user query, after answering it will also give you the its source of the answer, right? That's the reason why we maintain the metadata, because for grounding responses and for knowing the user from where this response is coming from. Now there are a lot of popular vector databases, like we have Pinecone, Vivian, Milvus, Quadrant, ChromaDB, and then Elasticsearch. There are a lot of vector databases that stores these vector plus metadata. Okay, now let's understand the so this is what vector database store, but how do you um, you know take your documents and update the vector database, right? This is known as ingestion pipeline. So the whole process of uh, storing your knowledge base in the vector database is the injection pipeline, right? So this pipeline involves your knowledge bases like documents. It can be PDF, web pages, or databases, APIs, Confluence, everything, right? And then we can also have a pre-processing stage where we clean the data, fix some missing data issues and all those things, right? And then we chunk them, okay, using some chunking strategies. You split them, um, you split these documents into different segments, okay, and then using embedding models you convert those chunks into relevant vectors, and then you store them in the vector databases. Like you have the vector and then associated metadata, this is called indexing, and then you store this entire data in the vector database, okay. And the best practice is always maintain metadata, okay, for source attribution, which means the LLM has to respond with the user query along with from where it has generated the response, the source of information, right? And also you need to keep updating this vector databases by re-indexing. Okay, what is the process of re-indexing is, let's say if you add more data here, okay, or if the existing data changes or gets updated, what you have to do is you have to again go through the whole process and then update the database, otherwise you will not have the up-to-date information, okay. For example, your internal HR documents may improve or change over time, okay. So if that is the case, you need to find the documents that got changed, and then you have to chunk the document again, embed, and then index and store in the updated database, vector database, so that your vector database has the most recent information, okay. Now once you have the vector database with latest information, so we can retrieve data for the user query, okay. For example, a user asked a question, how do I handle errors in Python, okay. So in order to find the results or the information uh, from the vector database, the question itself has to be converted into an embedding. So this is called query embedding, because I need to find the similarity between the basically um, two vectors, right? So I need to have the query embedding. So the entire query is converted into a query vector, and then this vector, okay, is compared with the other vectors, okay, to find the similar vectors in the vector space, right? So this will result in top k results, okay. So for this query there are multiple vectors that match. We call them as again chunks, okay. But in this also you can filter the outputs, okay, based on metadata filters. Like I want the responses from a particular date range, or maybe from a particular document, because your vector database will have embeddings from multiple documents, but I want the answer for this one only from very particular documents, okay. So what I can do is I can also use some filters to narrow down the results, okay. And then there is another component known as re-ranking, okay. Of course, for my question, the similarity search has resulted given me some 10 results, but not all results will contain answer to my question, right? So what re-ranking does is it will take all the these chunks, and it will again re-rank, okay, with my question to find only the chunks which are very relevant to my question, right? So in this case it has re-ranked from A, C, D, M. These are the chunks, okay. So basically from A to N are my original chunks. Using some metadata filtering, I filtered only A, C, D, M, let's say. Through re-ranking, it has the re-ranking model has decided that chunk C has maybe will have the better response for my question, or relevant information from my question. I will not say it is a result, it's a probably information that can handle, that can answer my question, right? So this chunk C is now sent to the LLM along with the original query. So this is augmentation step, Okay, so this is this is retrieval, and this is augmentation, and this is generation, where the re-ranked results plus the original query is sent to the LLM to give me the response, right? So this is a retrieval and re-ranking. But we also have something known as hybrid search, where instead of just finding the results, okay, which are semantically similar, I can also find the information vector database based on the exact keyword. Okay, so we have a ranking algorithm in the retrieval systems known as BM24 or bestmatch 25, okay, to retrieve a document to a given query, not just on the semantic search, but also on the keyword search. Okay, so semantic search may give me some results, keyword search may be giving me some results. So we can combine and rank to get the most relevant chunks, okay, that will give me the most relevant response, right? So in this case, you can see the question like best natural remedies to lower high blood pressure may result in multiple chunks having the answer to that question or information of that question. Okay, but using both the BM25 and semantic search, okay, we can re-rank in such a way that doc A contains both exact answer to my question and most relevant answer to my question. Okay, so we can re-rank them. So doc A has information about what are the natural ways to lower blood pressure. So other documents also have, but you can see they have remedies through herbal ways, through lifestyle changes, which may not be they may have remedies to lower blood pressure, but they are not natural. So through BM25 and semantic search, we find documents that actually is needed by the user, not the ones which may be useful but they are not relevant to the user query. Okay, now let's understand the RAG end to end. What is the flow is user asks a question in the natural language, then this question gets converted into a vector by the embedding model, and this is a query vector which will be the retriever would do a similarity search with the query vector and the the vector database, and then find the vectors which are close to the query vector, right? And when retrieving, it doesn't just retrieve the vectors which are similar to the query vector, but it will also retrieve the metadata, it will also retrieve the other information that is associated with the vector, right? We because we saw what vector database can store. It will store the vectors, it will store the metadata, it will store the actual chunks, everything, right? Now once we have the related results from the vector database, it is usually sent along with the user query to the LLM. So this is called augmentation. Now LLM will read the user query and also the augmented prompt to generate a response which is easy to understand, right? Not the raw chunks, but LLM will write it in most summarized way, so the user will understand the response. Now there are certain limitations of RAG, although RAG will give you the latest information from basically from the knowledge bases or through the from the vector database. The RAG always depends on retrieval quality, that is based on what information is retrieved from the vector database, LLM respond will depend. Okay, data freshness issues, so you need to keep re-indexing the vector database, otherwise you'll only have the old data. So if the data changes in the knowledge bases, you need to update the vector databases as well, right? And then context fragmentation, since documents are split into various chunks, the responses may not be actually consistent, so you need to find a very good chunking strategy so that the retrieved responses retrieved results from the vector databases makes more meaningful responses, right? And then context window limits, no action capability. Of course, using RAG you cannot do any external API calls or modify files or do anything. It is only the knowledge retrieval, not the LLM's capability to execute or trigger any workflows, right? And of course there is a latency involved, there is a cost involved, because during the ingestion pipeline you update the databases, there is a cost involved. And for latency, so the user query has to be embedded and then the similarity search has to happen to retrieve the results, so this will add to the overall latency as well. Okay, so there are other limitations. You can just pause the video and go through the limitations. Okay, so now we have seen what are various limitations in RAG. Let's understand what is MCP. Okay, so before MCP, let's say I have created an agent or AI agent or an LLM application. Okay, so for planning an entire trip. Okay, so for this AI to plan my entire trip, okay, so it has to know the weather, the flight services I existing, and then the hotel services that are there, right? But for LLM to get the information of all these things, right, so it need to call the external APIs. Okay, so every external service will have their own set of REST API, REST API models, their own ways of authentication, and all these things, right? So LLM application has to know all of these to actually do a meaningful job, like getting the information of whether actually booking flight and actually making the hotel booking. Okay, but what are the disadvantages in this case is, if any of the REST API model changes, right, you need to update the AI agent, okay, with the updated the REST API models. And also, in case if one of these weather service application that you are using, okay, is no longer available, you need to replace it with a different weather service, which also requires rewriting the AI agent. Okay, and also I mean, like, this is a vendor locking, right? So once you write the AI agent, it will only work with a specific flight service or a hotel service, because these are all hard coded into the AI agent. Okay, so what is the problem here is the AI agent doesn't have a standardized way of communicating with the external services, right? You always have to rely on the REST APIs for this. Okay, so now the model context protocol is created to fix this issue. So think of MCP like a USB-C port for all the AI applications, just like how we use a single USB port to connect multiple devices. Using MCP is like having a standardized method for the AI applications to talk to the external services, right? So MCP provides a standardized way to connect all the AI models to different data sources and tools. So this is just like REST API in web development. We have MCP in AI ecosystem. Okay, so we'll discuss about the architecture again later. So you can see here the AI agent application, which is probably an application written in Python, Golang, or else you can use any desktop applications like Claude desktop or VS Code or Cursor desktop or ChatGPT desktop version. So all these are like AI applications, right? Because you have an interface to talk to the LLM. Okay, so now these applications, now they can directly talk to the external services. Okay, for example, without MCP, so if you go to ChatGPT and ask it to book a flight ticket, it will not be able to do it, because it has no information on how to call those external APIs, what authentication and all that stuff. But what with MCP, how AI agent can actually do that stuff is, so we have a lot of external services, right? It can be databases, or it can be websites like Slack, GitHub, Stripe, or any flight, or you know hotel booking services apps, and all these services, right? What they do is they create their own MCP servers. Okay, so for example, for GitHub, let's say it has created its own MCP server. Okay, probably it is hosted somewhere. You can also run it locally in your machine. Okay, so every tool or the external service like database or anything has an MCP server. Okay, so when anything changes in the GitHub, right, like the REST API models or anything, they'll just release a new version of the MCP server. Okay, for example, for Slack there is an associated Slack MCP server. So what you have to do is you just have to talk to the MCP server. Okay, so if anything changes in the Slack, its MCP servers gets updated, but your AI agent need not know those changes or implement those changes, because already these are done inside the MCP server, which are managed by the Slack itself. Okay, all you have to do is, if you have to do something, the AI agent, if it has to do something, you just talk to the MCP server. Now MCP server knows how to handle its own application. Okay, for example, GitHub MCP servers knows how to talk to GitHub. Okay, so the connection between MCP server to basically the external services is via the MCP protocol. Okay, so we don't have to know about this as of now. Okay, the thing is, for example, let's say I'm replacing this with some flight booking service. Okay, so there is a company, let's say company X, which is providing those booking services for me. Okay, and I'm using that company services X MCP server. Okay, now my AI agent application has to talk to that MCP server X, so which will talk to the actual flight booking service to book the tickets, fetch the information of flight and all those things. In case if this company is no longer operating, so we can replace it with some other flight service and use its relevant MCP server. That's it. So your AI agent application need not be rewritten. Okay, so MCP server knows how to talk to their services, and you just have to talk to the MCP server. That's it. Okay, yeah, so let's see how MCP works in so let's say as a user. Okay, so I want to create some Jira tickets. Okay, so my query is like that: create Jira tickets. Okay, of course, I'm talking to my AI agent. Okay, my AI agent is nothing but the the one that talks to the LLM. Okay, so probably I've written in Python or some frameworks like LangChain, LangGraph, or anything like that, right? So the user asks a question, create Jira tickets for all the open issues, okay, in this repository in GitHub, and post them in project updates Slack channel. So I have to take the issues in a GitHub repository, create Jira tickets, and post them in a Slack channel. So that's my use case. So this query is sent to the AI agent, okay, that has the MCP client. So the MCP client is needed to talk to the MCP server. So in the previous example, your all the desktop apps are like MCP clients because they know how to talk to the MCP server. Okay, so in case if you're implementing any AI agent, you need to also use the MCP client framework or library. Okay, so here when a user asks a question, the AI agent knows what our MCP servers are connected to. Of course, through some configuration files, your AI agent knows like what all MCP servers are connected to it. Okay, so it's not a public repository or something like that. The AI agent will go and check. Okay, it is through config file. We usually config all the MCP servers. So AI agent, when it starts, so it knows what all MCP servers are it is connected to. Okay, so now AI agent analyzes the request. Now it plans the implementation steps. Okay, so the implementation is like, first it will understand, it has to go through GitHub, go fetch all the open issues from GitHub, and then create Jira tickets for each issue and then post it in the Slack. Okay, so first it knows like for GitHub it has access to the GitHub MCP server. Okay, and through GitHub MCP server, I mean like it is asking GitHub MCP server to get all the issues in a specific repository. So now MCP server will actually connect to the backend GitHub, okay, to fetch all the issues for this repository and gives it back to the the AI agent application. Let's not worry about tools and all, we'll come to it later. Now once it has all the open issues, it will connect to the Jira MCP server to create all the issues. Okay, and then later it will connect to the Slack MCP server, and then it will post all the Jira tickets and other stuff that it has created in this Slack channel. Okay, now you can see here, so this layer and this layer are completely different. Okay, so AI agent application is actually connected to the MCP servers through MCP protocol. Okay, I have not hard coded anything in the AI agent application. For example, in future I can even replace this one with the GitLab MCP server. Okay, and then I can ask it to fetch from GitLab. So AI orchestrator isn't need not actually have anything related to GitLab. Okay, so the all it has to do is know what all MCP servers are connected, and the client will do the rest. Like the AI agent knows like what MCP servers, what features or tools it exposes, and all that stuff are known to the agent. Okay, yeah. So coming to the MCP architecture, we have client server model. Okay, so client is actually your AI agent application. Okay, so which is also known as the host, and this client will talk to the MCP servers one-on-one. Okay, so when a user asks a question, so the host can establish one-on-one connection with the MCP server through MCP clients to process the request. Okay, so MCP servers are here. As I already said, for every tool there is an MCP server created by that tool. For example, Postgres has its own MCP server, GitHub has its own MCP server, like that. And these MCP servers are maintained by the these external services. Or else what you can do is you can also create your own MCP servers if it is not existing, and you can run it locally. Okay, so like MCP server can be containerized and run as Docker container, and then locally you run that Docker container, and then your AI agent can connect to that MCP server, and that MCP server which is running locally also has the ability to talk to the external service through REST APIs or something like that, right? Yeah. So this is an MCP architecture. So how your agent actually is able to create those issues or do something, right? So it is done through tools, resources, and prompts. Okay, MCP server, each MCP server, for example, let's take the case of GitHub MCP server. So it provides three types of primitives that model can use. Okay, so the first one is tools. Okay, as we already discussed, like using MCP server, like MCP server can talk to the like GitHub MCP server can talk to the GitHub for fetching the issues. Zira MCP server can actually create the issues in the Zira instance, right? So this is done to tools. Tools are something that we can use to take action. Okay, so tools are like, you can take as an example a function. Okay, so the using these tools you can do the operations like creating Zira tickets or posting Slack message, reading issues or creating issues, run database queries. So MCP server will expose all these tools. For example, for GitHub MCP server, creating a GitHub user or creating an issue, reading an issue, creating a PR, reading a PR, creating a branch, all these can be various tools that GitHub MCP server will give to my LLM or the AI agent. So AI agent can use these tools to actually do something, right? Like opening a PR, closing a PR, deleting a branch, all these things. Okay, now MCP server also provides something known as resources. So resources are read-only data that your AI agent can use. Okay, for example, it can give information about all the GitHub issues or some documentation. Okay, and all these things, and these resources can be static or it can be dynamic. Okay, for example, read GitHub issues can be provided as a resource, but the question that you may ask is, if I have a tool that will read all the GitHub issues, why do I need a resource for the same thing? So resources, if it is a tool, in order to get all the list of issues, you need to run that particular call every time. But if it is a resource, once that resource is updated with the information of the GitHub issues, that resource can be reused without actually going through the tools, right? So this is resources can be static, like information about your databases, what database table to use, how to structure your queries and all those things. So AI model can read and understand, right? There are also prompts. Okay, so prompts are like instructions that AI model can use. For example, I can expose basically a prompt to the AI model. Okay, something like code review checklist. Okay, so AI model wants to review a code. It has reviewed the code, but it has to show a summary of what it has reviewed and all, right? So now this prompt will give you that thing like how to you know, buck trash and then release notes and all those things, right? But we'll understand in with an example here. Okay, for example, user request summarize all open issues in repo, create Jira tickets and post a summary in Slack. Okay, for this one, you know, first the AI agent has to understand the user request. Okay, so maybe there is a prompt inside one of the prompt exposed by one of the MCP server. Okay, that explains how the model should proceed with that request. Okay, things like breaking that request into steps, what data I need, what tool I use. For example, for this you know, Zira and all, maybe there is a prompt that explains you know, the AI agent on how to approach this one. Now the model knows that it has to read the issues, create Jira ticket, so it uses probably resources, okay, to get the open issues, repository information or file contents of that repository and all. Okay, of course it can also use the tools to face zero open issues as well. Okay, now it knows that there are some open issues, so it uses the tools. So tools are actions that you know, the server provides, so that the AI model can call the tool to actually do something. Now, you know, one of the MCP server, that is GitHub, has tools for labeling issues, commenting on a PR or create issues or something like that, right? It can be Zira as well, right? So the AI model knows that there is a tool that can be used to search issues, so the AI model will call that tool to search issues. The same AI model can also use the create Jira ticket tool to create the Jira ticket, right? And finally, once it creates all the things, issues in the Jira, it has to post a message in the Slack. Now how do an AI model like, what format should an AI model use to post a message? Should it just post a list of PRs or anything like that, right? This is where a prompt template comes into the picture. Okay, so here there is a prompt that says how to post the response in the Slack, right? So you know, this is one of the prompt that explaining like list created Jira tickets with links, write a clear Slack summary. So there is a prompt that is explaining like how should you an AI isn't post a message to the Slack channel once the issues are created, right? So AI isn't also knows this prompt, like it knows that there is a prompt template existing or exposed by one of the MCP server, so it uses that prompt template to perfectly generate the response and post. If it you know, don't find this you know, prompt template, it may use its own knowledge on how to format the response and post it in Slack, right? Okay, now coming to RAG versus MCP. So you know, RAG is only for like getting the relevant information, but MCP is for taking action. So it has ability to talk to external systems, but RAG is only for reading the information to provide up-to-date information, right? So how it works is retrieve, augment and generate, but MCP uses resources for reading, tools for taking actions and prompts for guiding the model on how to approach a request or post the response, right? Source of data can be your internal knowledge bases, vector databases, but here the source of knowledge is the external systems, right? So these are some of the difference between RAG and MCP. You can pause the video and go through it. Okay, but by combining RAG and MCP, we can create more powerful agents. Example like analyze or GitHub issues and docs and create Jira tickets and post in Slack. But here you can also use the RAG and you know, MCP as well. Okay, how RAG can be used is so here um, for creating Jira tickets, probably like there is a specific format that is followed internally by the you know, organization, let's say. Okay, so that kind of information I can fetch through RAG, right? Even before creating these Jira tickets. Okay, like way to create and what format to use, and so that relevant information can be fetched through RAG, and through MCP I can actually take the actions. Okay, through MCP I can read issues, create Jira tickets, post them in the Slack, right? So by combining RAG and MCP, we can make a very powerful agent. Okay, coming to the final you know, slides. So let's talk about AI agents versus agentic AI. The AI agents are software systems that perceive input, reason about it and take actions, and they are usually created for a very specific goal. Okay, so unlike traditional AI which only generate text like what LLMs do, AI agents can also interact with external systems, okay, with the power of MCP, right? They are commonly used for workflow automation where we run the automation again and again, okay, to solve a very specific use case, or customer support where you ask a question and it responds, and something like data retrieval as well. Okay, so they operate with limited human intervention, and they can also take the inputs from external APIs and stuff. They will understand the user query using LLMs and reasoning. They understand the user query. For example, if I ask this AI agent to create a Zira ticket, probably it can create it, right? And also it has a memory to maintain context within the session, like what is the chat that it is having with the user, that is the context within the session, right? Basically these are reactive where you ask a question and it will respond, a very specific goal driven and task focused. Okay, so they perceive the information from the environment like the user input or reading from an API files or documents or some sensors or systems, and then they'll reason. So reason is the ability to understand the problem and start approaching the solution, right? So the AI agent analyzes the input and uses its knowledge and memory to decide what to do, because the reason why memory is required is maybe the agent is having back and forth conversation, so it has to know what it has responded before, right, in that session. So it can reason and then it can act by using MCP, so it can do something, right? For example, a customer service bot can for a customer service bot, it can be a user requesting to create to cancel an order. So it will understand the user query, and then it may use some tools to actually cancel that order. Okay, and then it will also give the feedback to the user that it has actually cancelled that order. So this is reactive, where you ask a question and then it will the bot will respond, right? So this is an AI agent. Okay, so AI agents can be created through various frameworks like LangChain, Llama Index, AutoGen, CrewAI, Haystack, and you can use any of the languages like Python, JavaScript, Golang as well. And since for the reasoning we need an LLM model, you can use any of the LLM providers. Okay, how the agent is actually created from scratch is you define a goal and use case, so identify the problem to solve, and then design the agent. So agent, like what inputs it gets, what LLM it should use, what memory it should use, okay, and what actions it can take, its feedback loop, so that it learns from the result. In case if it has done something which is not relevant for the query, and if user says that this is not the expected result, it also has to have that feedback loop to improve its responses over the time, right? And you need to define all these key components of an AI agent, and then you decide the framework, like which framework to use, and then you need to build and test that AI agent and deploy it and continuously monitor, right? So this is the typical components of an AI agent. Okay, you can also see the frameworks, the LLM providers, the languages, what tools it can have, how do you deploy. You can use Docker, Kubernetes, and AWS, GCP, Azure clouds. Okay, for monitoring you can use Langsmith or any other monitoring tools for an AI agent. Okay, so typical architecture includes the question that a user asks, the agent, the actual agent that you have written using the framework, and LLM can be used for reasoning, like it can be anything, any LLM, right? Okay, like the OpenAI models or Anthropic models or Gemini models. And then there is a memory that you need to use for the agent to remember the conversations, and then external integrations like the tools that the model so the agent can use to do some actions. Okay, yeah, so the same thing, customer support in action. Like a customer agent reads the customer email and extracts intent. So agent will understand what is the query of the user in that email, and then agent can take the decisions and automatically send a response based on the query, right? Now coming to the agentic AI, where while AI agents are used only for a specific use case to achieve very specific goal, agentic AI refers to AI systems designed to act with high degree of autonomy, where the human intervention is pretty much less, making complex decisions and executing multi-step workflows, okay, to achieve a goal. So here we don't give the agent a task, we give an agent a goal. Now it will do multi-step reasoning and do multi-step workflows to to achieve that goal. Like it also has the tools, memory, and reasoning capabilities, right? Agentic All agentic systems are agents, the AI agents, but not all AI agents are truly agentic, okay? And it is a shift from reactive chatbots where you ask a question and it gives the response, to proactive systems where the system can do end-to-end task, not just one task, right? So what makes AI agents agentic is goal directed behavior. So it will pursue objectives rather than just responding to prompts, okay? So if I just say book a trip, so it understands like booking a trip needs all those things like the information of the weather, the hotel booking and flight booking and all those things. So it pursues those objectives rather than just responding and asking the question back and forth. Planning and decomposition, so it can break that complex task into smaller steps and start executing them sequentially or in parallel. So it can also use tools to interact with external systems like APIs, databases, and all those things. And in order to maintain the state across various interactions with the user, it can also use the memory. Self correction, so it will evaluate the results and then improve those responses over time. Generally, agentic AI is a proactive, multi-step, and outcome-focused rather than doing achieving a single goal. Okay, so the same thing. So the perceive, that is the user input, and the brain, the actual LLM, do the actual reasoning, like breaking the entire goal into multi-step workflows. Okay, and then using tools, agentic AI can perform actions, and it achieves the goals through this process. Okay, and there is also feedback loops which evaluates the results, and uh, it improves over time. There is also memory layer associated to store the conversations as well. So this is one of the example, which is agentic coding assistant. Okay, so the main the task of this agentic coding assistant is to let's say I want to fix a bug. Okay, so that is the user query. Okay, so agent receives the, let's say I gave it a bug report, okay, or the logs or something like that. Now what agent can do is agent can understand and plan the step by step approach to solve this bug, right? So it can be like changes to the source code, rerunning the test, deploying it, and again checking in the application that is deployed, right? So what it does is it can search the code base, search for all the relevant files, and identify the root cause, like by checking the logs and from where the issue has come from, with what change this has after changing what part of the source code, like this change has come, this issue has come, and then it can write the fix, run the test cases, commit changes, and submit a pull request. And then it does this until a very specific goal is achieved. It doesn't stop here. Maybe after submitting a pull request, like even before submitting a pull request and committing changes, it may run the test cases and again find the issues, and again it will go through the whole process. So these are all goal oriented. They'll plan and decompose the entire requirements into each steps, and run them until a very specific goal is achieved. In this case, the goal is fixing the bugs, right? Not just fixing a single bug. So it has to do this entire process of bug fixing, running test cases, and all those things. Okay, so that's the difference. Like AI isn't is like they have a very specific task to perform, but agentic AI will have complex tasks, and that too they do it autonomously. Okay, so they are proactive. AI agentic AI is proactive, but AI agents are reactive. They generally answer to very specific user query, right? Yeah, so how it works and all, you can just pause the video and check. Now finally, reasoning in AI. Reasoning is a decision making engine inside AI. It is basically the step by step thinking process AI uses to move from a problem to the best possible action. Okay, so it can understand the context, analyze the data, draw conclusions, and take the best decision. Like understanding in the sense, understand the problem, context, and intent. Okay, and then collect relevant information from the knowledge bases. Okay, examine and break down the information to identify the patterns. Okay, so this is how it actually reasons, right? So it understands, it retrieves the data, analyze the query. Okay, and then use logic, rules, and experience to infer cause and conclusions, and then decide what step to take next, and then do the actual action. Okay, that's it for this video. I'll see you in the next one.